My last job was as a data scientist, as chief scientist at Causes, and Causes is the world's largest platform for collective action. One can go on Causes and create a petition, a pledge, or a donation campaign tied to a nonprofit. And I also mentor at Code for America. It's an amazing organization. If any of you are interested in being a fellow for next year, they are an organization that embeds engineers and designers into a city to design infrastructural platforms and analytics layers for municipalities. And I mentored 2 cities this term, and it was an amazing experience for me. So, what exactly is machine learning? Here are 2 very clear examples in perhaps the for-profit sector. Here's my Amazon page. I am about to buy Angry Birds Star Wars. The machine learning is obviously at the bottom here. Customers who bought this also bought, and this is based off of metadata, off of, Angry Birds Star Wars, the fact that it is a Kindle game, the fact that it involves angry birds and Star Wars. And so, as a result, some machine learning algorithm has selected, 8 applications that they think I should buy. And obviously, it's clear that the goal is to induce me to purchase more applications. Another example, LinkedIn, an amazing tool for networking and connecting with other engineers, data scientists, and entrepreneurs. Here's my LinkedIn. The machine learning is in that little corner on the top right, the people you may know. Given people that I'm already connected with, who are the next 3 people I should connect with? You can go to just my university classmates. You can go previous professional experiences. You can even go to friends of friends who've worked at some place. There's some algorithmic quantitative listing that defines a prioritization for this box. But these are 2 examples of for-profit applications, and there's nothing wrong with being a for-profit company, but there is our onus as engineers and data scientists is one of, we should use our highly skilled toolkit of things that we've learned in university and in professional life to make life better for the next generation. But before we get into that, engineers I feel are very rigorously defined. If I say I'm a software engineer, if I say I'm a hardware engineer or a systems engineer, that evokes a set of skills and tools and educational experiences that everyone can converge on. Data science is a very amorphous field. It's probably a rediscovery of what the 80s would probably say decision sciences or business intelligence. The anecdote goes, a data scientist is simply a data analyst in California. But what is a data scientist anyway? And so, I like this tweet as an explanation of what a data scientist is, right? They're better statisticians than most programmers, and they're better programmers than most statisticians. Sort of like a Jill of all trades, I suppose. And so, that's a pithy 140-character explanation of my entire industry, but can we codify this into 5 or 6 pillars? And this is what I came up with, statistical machine learning knowledge, engineering expertise or experience, academic curiosity, rough product sense, storytelling, and a catch-all I call cleverness. And so Valve Software is an amazing software company in, I believe, Bellevue, Washington, and they create games that I play. And their HR handbook has this idea of a T-shaped employee. That is, someone who has a wide breadth of skills, but there's one vertical in which he or she can hang their hat on. They are the one person who excels at software engineering, the one person who excels at HR systems or regulations. They're the one person who excels at buying pizzas. And so the 6 pillars I named, I think it looks like this, right? Academic curiosity, storytelling, product sense, engineering experience, and cleverness. Well, these are all things we should have some passing experience or expertise in. But the statistical machine learning knowledge, that is our ability to codify complex algorithms into code to explain phenomena in some worldview, you really have to know that. What differentiates a data scientist from a data engineer or a data scientist from a DBA is really the ability to take large amounts of data and turn it into some sort of a training set such that you can train a model to produce some explanation of what is going on in the world. So to dig in further, I define academic curiosity as the desire to go beneath the surface and discover and distill a problem down to a very clear set of hypotheses that can be tested. One thing I love about data science is that we can take the academic sort of latitude we get in university and apply this to industry. Obviously, as we work in companies that have clear bottom line revenue KPIs, this academic curiosity can only go so far. But in data science, these people are given amazing latitude in figuring out, well, what are the next 5 steps that we can achieve with our data? Or rather, what are the next 5 years of vision or societal change that we can perform given the data we've aggregated from user behavior or just the news in general? Storytelling, the ability to use data to tell a story and to be able to communicate effectively to non-technical stakeholders. This is a page taken from a clustering analysis in the UK called PRISM, very aptly named, but the UK has taken the entire database of census data, credit scores, and qualitative survey data of lifestyle, and have segmented the country, the United Kingdom, into about 90 clusters. And one such cluster is shown here, golden empty nesters. Without telling you anything else, those 3 words evoke a picture of some sort. It tells you a story. The pictures also tell a story as well, and that's before I even go into the quantitative brunt on the right side, that they make between 25 to 35,000 pounds, that they tend to be highly educated, that they tend to live in very highly dense urban settings. The ability to distill quantitative data, algorithms, processes, structures, and turn that into a qualitative story that is not just convincing, but actually rooted in truth, is an onus we all share. Because we can tell a great story and actually lie quite a bit with statistics, and yet we've seen that in the news. But just because we have the unique ability to tell a good story, and we have the unique ability to munge data and have a truthful worldview, does not mean we get to abuse either when we communicate this to a non-technical audience. Product sense, again, the ability to use this story to create a new product or change an existing product in a way that improves company goals and metrics. A very for-profit explanation. But again, if you notice, the goal of this, what is an 800 by 20 pixel box, is to get me to buy more things. And it's actually exceedingly good at this. I think I bought 3 of those afterward. Whatever product you ship as a result of these quantitative algorithms, well, better drive some company metric. And for-profit, that's obviously revenue or engagement. For nonprofit, that is just some societal change or societal good. If we look at the new healthcare.gov, the new marketplace, there are clear KPIs of getting people to sign on to an insurance plan that works for them. And by nature of being a web product, they're pursuant to the same goals and KPIs that any web product has. They have the same engagement metrics as Facebook. They have the same retention metrics as Twitter. Statistical machine learning knowledge, the domain expertise required to acquire data from different sources, create a model, optimize its accuracy, validate its purpose, and confirm its significance. And this is one such workflow of how to turn data into models. You take some data, you play around with it, you scale it, you split it up, you have one training set and one validation set. With the training set, you build a model off of that. In Excel, this could be a linear model. In C, this could be using LAPACK to create a deep decision tree. Whatever you do, you want to validate the accuracy of this model by taking the predictions you produce from this validation set. This is the set of data that wasn't trained in this model, and thus is new data. And so when you take a model, or when you take a set of data, train a model, and validate it with a new set of data, and it's fairly accurate, you now have a model that represents a bit accurately the worldview at large, assuming your data aggregation techniques were valid. Engineering experience, the coding chops necessary to implement and execute a statistical model and its validation. There are several languages or several lingua francas in data science, Python, Java, Pig, Scala, Clojure. This is a very naive example in R of producing a random forest decision tree model. And the ability to not only understand the quantitative underpinnings of an algorithm, but to be able to encapsulate that in code so that it's reproducible is probably the hardest skill for any data scientist. they tend to come not from engineering, or possibly from engineering, but from mathematics and physics, from biology and other life sciences. And so as a result, the software engineering skills are not probably as good as you guys. And the catch-all cleverness, the creativity to do all these things on a deadline and on constrained resources. I think, for those of us in the industry for a couple of years, we all know that there's never an ideal situation. We always have constrained resources. It's always due yesterday, and it has to be due, or it has to be production or web scale or production ready. And also, you have 9,000 stakeholders, and they all want different things. The ability to take all of that and produce something that is just 80% good for everyone, but also increases metrics and is accurate and tells a story is just an amazing skill to have. And it's really hard to codify what exactly that is. And so I've called it cleverness. And so, with a better idea of what data science is, or at least a better idea of what I think data science is, we're going to cover 2 case studies of how we use data science for good. One from a nonprofit perspective and one from a for-profit perspective. And so in this case study, we take a look at the Heritage Provider Organization. This is a nonprofit physician network that serves most of Southern California in the United States. There's 2,100 primary care physicians, 30,000 specialists, and they have probably the state's largest comprehensive EHR, electronic health record database that's used and stored in their proprietary infrastructure. And so they held a competition before we get into the competition, just some primer on hospitalization in the United States. In 2012, 71 million people were admitted into the hospital. Of these 71 million people, 11 million were classified as unnecessary. And this was about a $30 billion bill in unnecessary expenditure. The majority of this, the majority of these false admissions were made by general practitioners and managed care organizations, HMOs, PPOs, what have you. So the Heritage Provider Organization thought, can we hold a competition for machine learning enthusiasts and data scientists to create an algorithm or a data-driven approach that general practitioners can use in assisting their diagnoses and decrease false positives? I'm not going to create a linear regression and have that replace a doctor, but I can create a complex model and have that inform a highly skilled medical professional in what's going on. And so, the raw data looks a bit like this. There's a members table, highly anonymized. The UID doesn't actually match to your social security number or anything, but it tells you your age and your gender. The RX table, prescriptions, how many drugs you've been prescribed in the last year. Your claims table, labs table, and the number of days you spent in the hospital. And for the sake of this competition, your goal was to take the first 3 years of patient data and create a model that predicted how many days you'll spend in the 4th year. And so, we take a look at some of this data, and there's a lot of munging and data cleaning that needs to be done. This is a distribution for, I believe, broken bones. How many people were admitted into the hospital for a broken bone, or rather, how many people were diagnosed with a broken bone. And we take a look here, and it's highly skewed. It's a power law. If we wanted to run this through, say, a linear regression, or we want to run this through a logistic regression, or anything assuming a normal basis or normal kernel, then we have to normalize it or apply some sort of mathematical function to create a normal distribution, which we're all very familiar with and would absolutely love. So if we just take the log of this, you'll see that this power law now becomes, somewhat of a normal distribution. On the left side, we see the actual histograms. On the right side, we see the quantile plot, the QQ plots. That red line denotes the normal distribution. The black dots denote the actual data points themselves. And so in this case, after applying a log transformation, we see that the data points are slightly more normal, and that's good. In fact, we know how good it is because how closer it is to a normal distribution. This is one of about 3,000 metrics in this data set. In terms of, this is just broken bones. There are also 300 different conditions you could be diagnosed with. There are 30,000 different physicians who all have different specialties. And there's, I think, at least 2,500 venues in which you could be admitted to, whether it's a hospital car, an office, inpatient, outpatient, so on and so forth. But for now, let's just take a look at 2 metrics. Age is the first one here. The thesis is that, well, older people tend to be in the hospital for more days. That's a really sad realization when you think about it for me. But I didn't mean that as like a truth. But this model tells us that the older you are, if we look at the segmentation, we take a look at the distribution here, we see that the top half is the age distribution of all members. The bottom half is the age distribution of all members who spent at least one day in the hospital. And this is slightly skewed to the right. Our second metric that we look at is something called the Charleston Index. And this is an index score that's given to you at the time of diagnosis or admission. It's a score from 0 to 5. 0 is given to a completely healthy person. 5 is given to someone who has a very, very high risk of death. And another metric I took a look at was the number of claims. And the idea here was that as the number of insurance claims increase, so too do the number of days you spend in the hospital. And so we took a simple linear model of, well, the log of days in hospital is proportional or about equal to some coefficient times the age at first claim plus the number of claims. So by simply looking at the number of claims, we achieve a root mean square log error of 0.47. So we extrapolate this out, we are about 63% accurate. And with respect to this competition, we are 82nd out of 255 teams. What that told me was that even a very simple model of 1 or 2 metrics can be quite predictive at scale. And so we want to find a way to add all the variables in. And there's like 30,000 variables. But we want to also prevent this concept of overfitting. And I'll explain what overfitting is in a minute. And so I won't go over this slide in too much detail. But the idea here is we want to recursively select on features that we know are predictive. Whether a female is pregnant or not is probably a predictive feature of whether she will go to the hospital. Whether I have a cold is probably not a predictive feature of whether I'd go to the hospital. And so we can encapsulate this in code and pick each feature, or rather a basket of features, run a model, evaluate its performance, and then take another random basket. And through some genetic algorithms, we'll converge to a basket that works, or is rather the most predictive. And so we can see here on that bottom that we take a basket of 190 predictors. This include broken bones, pregnancy, age, your Charleston morbidity score, the number of claims, venues. Some venues were trauma centers, some venues were offices. Offices are probably less predictive than trauma centers in how many days you'll spend in the hospital. We shipped the model with 190 variables in a linear regression, and we're now 35th out of 410 teams. And so, this is about the max performance we can achieve with a simple linear regression. This is something that we can create in Excel. Just a primer on decision trees. We want to create a very complex logic model of logic choices, where here's a very simple illustration of a decision tree, where, well, if you're male, then it goes to the next branch. Yes is to the right, no is to the left. And so, are you male? Yes. Do you have prostate cancer? Let's just say yes. That's 2.4 days you might spend in the hospital. If no, then 0.21 days in the hospital. If you're not male, if you're pregnant and you delivered in the hospital, you probably spent 2 days in the hospital that year. If not, 1.83 days. And so this is one of probably millions of decision trees you can create that hopefully encapsulates the 190 variables that we empirically found were the most predictive. And so we did this again, and we realized there wasn't that much of a performance gain. We went from 35th to 34th, and we only create a 2% increase in accuracy. And there was another problem as well. We grew 500,000 of these decision trees on a single desktop, and it took about, I think, 3 days to train this. And so we're going to need about more. We could throw more cores at it, and we can also parallelize this. And so by parallelizing this against a multi-core array of boxes, say you had like a server farm of 300 machines, we had 10, but each one had 30 cores, and we ran a decision tree that split the data set into 30 different smaller data sets and created decision trees. Well, now we have something that's a little bit faster. So that was the best approach we could come up with. And just to clarify what overfitting means, right? If you take a look at this picture on our right, we have a model that is very simple. So the classification problem here is that you have some red dots and you have some green dots, and you want to identify whether that yellow dot is green or red. And so imagine if the red dots were people who went to the hospital and the green dots were people who didn't go to the hospital. So if we take a look at that top left picture and we see a straight line, well, this is a model that's very simple. In this case, we have a huge classification error where maybe below the line, everyone goes to the hospital, and above the line, everyone does not go to the hospital. And we know here that that's very inaccurate. On the top right, we have a very complex overfitted model. The line represents the model boundary here. And in this case, we've achieved perfect accuracy with our training set, in which all of the green dots are clumped together. And so all the green dots are people who perhaps went to the hospital, and the red dots are people who did not. But now this yellow dot is now classified as someone who did not go to the hospital. And so the ideal model is some mixture between granularity and generalizability, some model that encapsulates as much of your data set as possible without explaining the random stochastic errors. Right? There is some random error that happens with every feature in our data set. A model that even explains the heteroscedasticity, or rather the very minute randomness, is a very overfit model. And so some ways to overcome this. As I mentioned, this idea of splitting up a test and training set into two. We can also split this n times and create a smoother, more averaged model. But this is down in the weeds, and I won't cover that. But the whole point of this is that with the overfitting techniques, the overfitting mitigation techniques I explained, and the decision tree parallelization, we ended up with about a 73% accuracy, and we achieved a final scoring of 9th place out of 1,400 teams. And the goal here was to take this model and to create an algorithm that predicts whether a patient has to go to the hospital or a patient has to be prescribed some drug. And this is now, our research is now encapsulated with is now with the Heritage Provider Network. And they're trying to figure out a way to take the models from each team and generate a generalizable model that can assist general practitioners in diagnosing a patient as hospitalizable or non-hospitalizable. I thought that was a pretty good case study in how we can use machine learning and data science into either saving lives or saving money in terms of false hospitalizations and in terms of cost savings for patients. I think another version or another case study I'd like to cover is this idea of collective action. And so at Causes, Causes.com is an online network where one can create a petition, a pledge, or a donation campaign to a nonprofit. And the thesis of Causes is that collective action is the major driving leverage in achieving societal change. And so one of the levers of societal action is through this idea of creating a petition to produce some sort of tipping point. And so a great data science problem would be to predict the probability that someone will sign a petition. And so we want to take our massive amounts of data at Causes to create a probability that someone will sign a petition or take a pledge. And we'll be looking at a very specific type of petition in just a minute. But the goal is we want to create a model that predicts a probability, and we can use this model to predict the future probability for any new user coming in. And so here's the petition we'll be looking at. Demand Congress investigates sexual assaults at Lackland Air Force Base. Lackland, Texas has an Air Force base, and there was a sexual assault case or a sexual assault incident that happened several years ago. The gunnery sergeant wanted to reopen the case, and it was denied twice. And so this person went to Causes, and this person went to change.org and many other petition sites to create a petition to get enough signatures and public awareness into reopening this issue. And so we acquire a bunch of data from how we use websites. They can either come from Facebook, which represents demographic data. They can come from behavioral metrics, where we click on Causes.com. and they can come from our IP address, which represents a location. We store this in a database, and when a user signs a petition, we record that behavioral credit in another database. We aggregate and parse all these databases, or we ETL them into one centralized database so that when we query them, it'll be a relatively easy thing to do. I've already covered a normal distribution, but just in case, a normal distribution explains many general phenomena in biology and in sociology. The idea here is that there is a peak, and that peak represents the general mean. The probability that you will stray from that mean is the same in either direction. And this could represent IQ. This could represent the number of hot dogs you can eat on July 4th. This could represent a whole bunch of things. And so our goal here is to take some behavioral metrics, say, whether you sign the petition or not, and your demographic metrics, your age, whether you're female, whether you're a veteran, whether you're from the South, and figure out what are the most predictive features that goes into signing this particular petition. And so our response variable, the feature that we care about in this model, is whether they sign that petition. That is the action in which we want to optimize on. And so in this case, we'll be using a logistic regression. Logistic regression is a model that returns a value from 0 to 1 and assumes a very nice S-curve using something called the legit curve. But here's the slide that actually encapsulates these results. If we ran this in R and we took a logistic regression of age, whether they were female, whether they were a veteran, or whether they were from the South, we see that the intercept, that first number, estimate 0.019. That is, without knowing anything else about you, the average user on causes has about a 2% probability of signing this petition. Age, 0.002. That is 0.2%. You add 0.2% for each year of age you have. So if you're 10 years old, this is a 2% risk increase that you'll sign a petition. If you're 100 years old, this is a 22% increase. Another way of saying this is that the older you are, the more likely you are to sign this petition. If you're a female, your risk of signing this petition, not risk, but your probability of signing this petition decreased by 10%. If you were a veteran, this increased by 67%. Veterans were the most enthusiastic about this petition. And if you were from the South, if you were from one of Texas, Georgia, Louisiana, and 3 other states, I forget, it added a 34% probability. I'm really sorry for forgetting that. But this was 4 features that we found sort of serendipitously. And of course, the final model included 30 more behavioral metrics about this particular petition. And when we ran this against our test set, or we ran this against new data, we determined that, for someone who signed the petition, the model predicted that would be 85%, 93%. For someone who didn't sign the petition, 39%, 48%, and then again, for someone who signed the petition, 72%. That's not that bad. In production, we just used a boundary of 0.67%, or 67% rather. So 67% was the boundary in which if it was over 67, you were probably likely to sign this. If it was below 67, you probably weren't. Well, why do we care about this anyway? If we knew you were likely to sign the petition and you hadn't signed it yet, well, this is no different than the Amazon recommender. We can now send you an email saying, hey, here's something you might care about. Instead of buying another Angry Birds title, here's a petition about a feature or a topic or some locale that you might care about. And the goal here is to raise public awareness and to get people to sign a petition online. And as a result, we get people from all over the globe signing petitions. And these people represent social networks or social capital that they can use to invite other people. This is a visual diagram of who invited whom to sign this petition. And I thought it was pretty poignant in how we represent data to tell a story. If we take a look at the man on the far left, Stephen Price, 22 people invited, 30 people total reached. Stephen Price was a veteran in the Iraq War. If we take a look at the top here, Kenny Peters. Kenny Peters had a son who died in Persian Gulf. Jen Lee Norris, up top, has a daughter who's actively serving in the Navy. Sasha Rose Quinn has a daughter who's serving in the Air Force. Each person who has a large social reach and is inviting everyone on their contact list has some visceral connection to the topic at hand. How we use that story and encapsulate data rules or algorithms that predict the probability that this person would be interested in this content was a huge win for us. And so, we've only talked about what happens online. To close that out, the case was reopened. The person who created the petition on causes, change.org, and other petition sites, whitehousepetitions.gov, aggregated 3.7 million signatures, just dropped a large box of papers on the judge's desk, and the case was reopened a week later. So we take online actions, behavioral metrics that we put on a database, and we want to map them to offline actions, things that actually happen in the real world between me and you. And so we take a look at the inputs, what goes in, the activities, what happens, the outputs, the immediate results of this, the outcomes, the midterm results, and the impacts, the long-term results, significant and sustained change, effects on root causes. The immediate results, well, the case was reopened. Midterm results, we are now incentivized to believe that whenever something happens, we can create a petition or a pledge or a donation campaign to create some immediate result. And the long-term results of this is that policymakers, politicians, and people on the other side of the fence are now incentivized to follow public will, to not close cases that are suspect, to basically be more accountable to their constituencies. And so here's another example, boycott Chick-fil-A. Chick-fil-A ran there was a pull quote from someone from Chick-fil-A that was slightly homophobic, and someone on Causes created a petition to boycott Chick-fil-A. This was at the time the petition was created. Here we have 9,000 signatures within about half an hour. By the time it was finished, 1.5 million people had signed the petition. So we know it's not 0 people who boycott Chick-fil-A, and we certainly know that it's not all 1.5 million people who signed the petition. But somewhere between 0 and 1.5 million, we have a number of people who actually boycott Chick-fil-A. We have a hard economic cost to Chick-fil-A. That is a major data problem where Causes is still trying to investigate, and indeed many nonprofits are trying to investigate. What is the actual online or offline impact of a petition like this, where there's an economic cost? How do you survey people? You can't call them up and say, did you actually boycott Chick-fil-A? Because if they didn't, they're not going to answer the phone. Here's another example. Get NBC to cancel inhumane hunting show Under Wild Skies. If we just ignore the lack of the article in this title, we know that Under Wild Skies is a TV show on NBC. And during one episode, there was a brutal execution scene of an elephant with a rifle. And someone was so incensed by this, this person created a petition on causes, change.org, petitions.whitehouse.gov. Within a day, 104,000 people signed this petition. Within 30 days, it was 4.3 million people. So 4.3 million people want a show canceled. Does it actually get canceled? Well, we can see these people are so incensed, they invite other people. And when these people invite other people, celebrities take notice. And when celebrities take notice, we see sort of a minor news agencies pick it up. HuffPo could be minor or major depending on your outlook, but here's a HuffPo article. HuffPo covers it. Now we have industry trade magazines covering horrendous practices as surfaced by celebrities, which were surfaced from people who invited other people on a platform like Causes. And the goal here, or the outcome of all this, is that, the NRA loses an advertising platform, a realized economic loss. NBC actually cancels the show, which results in some amorphous animal preservation. And so that's something that we need to follow up on. But we now have 107,000 inviters, people who invited the 4.7 million people who are now ready to mobilize again. That is a non-trivial result in all of these examples. And that's one of many ways in which a for-profit company like Causes could affect social change, or change.org. So, those are the two case studies I presented, and those are two of hundreds and hundreds of ways in which nonprofit organizations, NGOs, and for-profit companies can use data science to optimize for societal benefit rather than clicking on ads or clicking on purchases for social or virtual goods that you'll never use again in 3 months. Thank you.